So I'm curious, hands up if you've gotten AUC. Yeah? Do you want to just shout out what AUCs you got? What you got? 8.4? What do you got? 79? What you got? 82? 86? Anyone else? Anyone else? All right. So with random forests, with that data set, playing around a little bit, optimizing the hyperparameters, I got to about 0.93. And in the paper, we had a little bit more training data, and we also had better features, more precise features. So you can get up to about 0.978 or so, 0.98, which is pretty good. So this problem is very solvable. Okay, so by popular demand, I had no intention of talking about deep learning at this workshop. Still some murmurs. Are we ready? I know this tutorial is fun, but trust me, this is also fun. So I wasn't going to do deep learning at all. One, because I haven't actually used it that much in my own research. I'm involved in a couple projects with it. Don't use it too much. Two, I would probably need a week to do it properly, never mind a day. And I really wanted to get through the fundamentals of machine learning with you. So this is something I thought, you can do it yourself. But there was some demand, so I put together just a few slides on what deep learning is, and just to give you sort of a feel for the idea behind it, rather than any kind of real technical depth. So there's been a revolution in machine learning over the last few years. Now, I would say about the last, 7 years or so, maybe less than that. And the revolution has been entirely because of deep learning. And really because of one algorithm that they came up with. And it's actually solved some problems that have been unsolved for decades. I just realized I forgot to put this in. Gonna really entertain you guys. Ooh, that's not supposed to happen. Okay, we're okay. Or is it the connector? Do you want to just take it out and put it in again, maybe? Turn it off and on again? That's mine, yeah. Oh, maybe that's not the right thing. Okay, we'll have some technical difficulties. So really, the deep learning revolution came about because of one algorithm, which is the convolutional neural network. There are other deep learning algorithms, like recurrent neural networks, but this is the main one. And the idea is, let's build a neural network that's really deep, maybe tens of layers deep, hundreds of layers deep sometimes. Now, if you try and do that with a standard multi-layer perception that I taught you guys this morning, it falls down. It really doesn't work, because you've got loads of parameters, it's not really that well constrained, and it really just, everyone kind of knows there's no point doing more than 1 or 2 hidden layers with a normal MLP. So the key insight with convolutional neural networks is that with a very particular type of network, you can actually do this. You can go deep. Is it okay?
Well, it looks okay here, but it's not showing on the screen.
There you go. All right. So the network's kind of, this is how a deep network would look, but this is really a deep sort of normal network. And the key thing is that these things are able to learn hierarchical feature representations. So if you give it images of faces, some layers will be sensitive to these kind of weird, edgy features that might be a bit like eyebrows. Here you can start seeing there's eyes, there's noses, there's ears. And if you go out to the top layers, you can see broad features, entire faces. So this is one of the reasons why these algorithms are so good at image recognition. They actually solved the image recognition problem, which has been unsolved in computer science for decades. Okay, so what do you have? This is a normal multi-layer perceptron like I taught you this morning. The key difference is the structure of the neurons in convolutional neural networks is very different. One concept to keep in mind is that everything is now three-dimensional, and the dimensions are very important. If you try this yourself, if you try constructing convolutional neural networks, the dimensions of all the layers is a really important thing to keep in mind. They are designed to work with images. They really are fundamentally designed to work with images. It doesn't mean they don't work with anything else, but you have to make your other stuff kind of look like an image. So it has to have a width and a height, and the depth is usually like the channels in an image, like RGB. So the key thing is that each neuron, instead of being connected to every other neuron, you remember there was a weighted sum of all the other inputs of the previous layer, they're now only connected to the local pixels or whatever, the local elements of the previous layer, right? So this is why we start talking about neurons as filters. And what you do with this filter is you slide it across the image, right, with some kind of window function, compute this weighted sum, right, just like we did before, but now you're only computing it in a local space, and see how much it activates. So the concept of activation is still there, right? But now, instead of just saying, okay, how much does it activate connected with everything, we're saying, how does it activate at a local point in the image, right? So there's this concept of locality that's very important. So if you go on this website, I think it is, there's a very nice illustration of this moving around the image and producing the activation, what's called an activation map. So that's what you get at the other side. For each of these filters, you get out a map of how it activates, right? And that's when you put them all together, you get maps of, these are each filters, and these are the things that they are sensitive to, kind of. This is very hand-wavy, in case you haven't noticed. So you get out these features from these maps, you get out these features, they're called deep features. And these are the things that each layer in the network is sensitive to. Yeah.
Okay. No, with your last slide, the convolution kernel, does that change as a function of position, or is it fixed?
So it doesn't change as a function of position on the image,
Yep.
right? So the filter will be the same, but you may have different filters in different layers,
Okay.
right? So you can even have different size filters. Sometimes people do more complicated things, have more complicated transforms in their filters, yeah. So networks look a lot more complicated than what you saw this morning. And the convolutional layer that I've just described is not the only kind of layer you get. You have pooling, you have fully connected layers. Fully connected layers are like exactly like we had this morning, where everything's connected to everything else. You have dropout, which isn't shown here. You have softmax. And each of these has technical definitions that it's worth really understanding what they're doing. So this is the network that I would argue solved the image recognition problem. It's called AlexNet. And it kind of won the ImageNet competition a few years ago. And there are more and more complicated networks that have been built. Inception, I think, is even more complicated than this. So these architectures are very complex. And there's an art. It's a real art form. It's not a science for how to develop these architectures. So you can kind of see the complexity involved in building these networks. So on the repository, there is an extremely simple tutorial using TensorFlow, well, actually using TF-Learn, which uses TensorFlow, to run a CNN on this data set called MNIST, which is just handwritten digits. It's a very standard machine learning data set. So you can have a look at it, and what you'll see is it's actually very simple in terms of number of lines. You know, to do this, it's like TF-Learn I can't remember, but it's TF-Learn.convolutional, and it will make a convolutional layer. So building the architecture is actually quite easy. Figuring out what the hell it's doing is a somewhat different story. So if you have a look at this, this can get you started. If you think maybe I want to use deep learning in my research, this will get you started. There are a number of packages. Keras, which is Keras, is also very nice, and I've used it in the past. TensorFlow probably has a much bigger user base, and I mean, it's written by Google, so it's used quite a lot. So the reason why deep learning is hard is you need a huge amount of data. You can end up with billions of parameters in these networks. Now, they are not billions of uncorrelated, unconstrained parameters, so it's not actually as hard as it sounds because of various tricks that get implemented, but it is still hard. So, for instance, there was a paper that came out that did the same supernova classification problem with the same data set using deep learning. And they managed to get the same AUC as us with 10 times the amount of training data. That's what they needed. It was a minimum of 10 times the amount of data. So it's really for the case where you're drowning in data and nothing else has worked. That's what I would say. Only really turn to the deep learning when you've tried other stuff and it doesn't really work. It's computationally really horrible. Like if you run that deep learning example notebook, I've done 2 epochs, which is a very short amount of time to train the network, and it's a very simple problem, and it still takes like 5 minutes on a computer versus what you've seen with scikit-learn, where it trains like this. So you really have to have a GPU to be able to really optimize these things and use them well. Getting the architecture really is an art form. If you think it was hard to kind of decide what hyperparameters to use for random forests or k-nearest neighbors, this is a nightmare. Really, there's like an infinite number of things you could do, and they could all be fine or all be terrible. And it's a bit hard to interpret them. So how do you solve these problems? Well, to get huge amounts of data, you can use a lot of tricks like data augmentation. What they use in image recognition is they'll take an image and they'll apply transforms to it. Because a cat upside down is still a cat. Or a cat slightly zoomed in is still a cat. But the network doesn't know that. So it's able to use that data, even though it's the same data, it can use it again and again. So you can augment your data by quite a large factor. And this is done a lot relatively safely in deep learning. You need a GPU? Well, you can mitigate that by getting a GPU. Sorry, there really isn't another way around it. If you start this and you have no idea what architecture to use existing architectures. Start with something like AlexNet, especially if you're doing image classification. Don't go off trying things crazily yourself. Start with what already exists and see how well it works for your problem, and then make little tweaks. I also just want to mention there's a very, very nice paper that came out this year by a head of group and a student, where they actually use genetic algorithms to automatically determine the optimal architecture for your problem. And it's actually very, very powerful, very general. It obviously takes a long time because it has to run these things over and over and over again, but potentially takes less time than it would take you fiddling around by yourself. But unfortunately, I don't think the code is quite out yet, but keep an eye out for it. It's called Eden. The hard to interpret thing, well, that's a whole research topic on its own, and people are actively researching how to interpret these things. Question, yes?
Is there a measurement to know when you have enough data for the training, or how do you know?
That's a very good question, and no. I mean, it's the usual thing of, if you have too little training data, you're going to be overfitting. So the standard procedure of keeping aside a test set, checking your metric, making sure you're not overfitting. And there are sort of heuristic calculations you can do, which some of the packages I think do, about how many parameters you have, and for a chosen architecture, how many parameters are in there, which can guide you for how much data you might need, but it's very problem specific. Yeah.
So about this problem of hard to interpret and the black box thing, if you know the architecture of the network, we know how it's trained, and as you show, like you know the futures. So I don't know, for me, it's like feel kind easy to think that you're trying to match the patterns that you have and you filter the data. So
Yeah, and
doesn't
and this is what people do. You know, they'll make activation maps in the various layers to see what is it actually looking for. But at the end of the day, when you look at those activation maps and what's actually going on, may be completely different. And there's been a lot of literature on interpretation, and you can do things like change one object in the training set, and it can change those activation maps. You know, it shouldn't be so sensitive to that, but it does. So, you know, yes and no. Like, you can feel maybe this is quite comfortable, but when you really start digging into it, there's a lot of issues around interpretability. Okay, so I'm going to move on, and then at the end, so just in the interest of time, and at the end, if you have more questions, you guys can ask, because I kind of wanted to show off a bit, because we've seen a lot of really great statistics the last 3 days, and showing the power of Bayesian statistics, and I am very much in the same camp that if you have a model, and if statistics works, do it. Don't do machine learning. Your first port of call should always be to do a nice, proper Bayesian model. But there are a lot of problems that statistics has not been able to solve, that nothing has been able to solve, that deep learning has. And so I want to show you some of the amazing real-world applications of deep learning. Here's the first one that I think is pretty amazing. You have a convolutional neural network which not only identifies like a child, man, but will identify individual objects in an image, coupled with a recurrent neural network, which is a different type of neural network that's designed to work on sequences, like time series and specifically language. So the recurrent neural network comes up with a sentence to describe the image. So we've got construction worker in orange safety vest is working on road. Computer came up with that. It's pretty good. 2 young girls are playing with Lego toy. Seems pretty reasonable to me. Technically speaking, is everyone aware of what the Turing test is? You all heard of the Turing test. So Alan Turing proposed this because one of the problems is if we're starting to talk about AI, well, we know what the A is, but what is the I? This is a philosophical debate we can have. So Alan Turing proposed a test which said that if you had some kind of computer program that could, if it could mimic a human, or if it could convince a human that it was human, it could be considered intelligence. That's sort of a summary of the Turing test. The technical definition basically said that it had to convince 30% of some people interacting with it that it was human, right? Technically, the Turing test has been passed. 2001. There was this chatbot with the bizarre name of Eugene Gustman, who was portrayed as a 13-year-old Ukrainian boy, which is supposed to get around all the weird language issues. And so obviously this chatbot, there was a sample of people interacting with a computer. They didn't know if on the other side was a human or this chatbot, and they had to decide, is it human or is it a machine? And 30% of people thought it was human. Now, nobody's parading in the street. The Turing test is passed. We have AI. It's, we can all retire. But it is interesting that technically the Turing test has actually already been passed. This is a fun one. Okay, everybody go to whip out your menti.com. And go to a blank screen. No, still a blank screen. So, wait, sorry. Does anyone have any questions while I'm busy with this? Yeah? I'm listening.
Microphone is on its way. I just wanted to double check my understanding of what made deep networks possible. And it was that basically compared to old-fashioned neural networks, you could assume that a lot of the weights were zero. And then it was actually possible to train them even though you had all these layers. Is that possibly what it's got to do?
Sort of, yeah, because essentially, because each neuron is connected only locally rather than across the entire network. So you don't
Yeah.
have to work up the weights for every single pixel. It's just the weight of the filter itself and
Yeah.
how it's,
Cool.
how it activates. Okay, so this should be. Can everyone see this? Okay. Okay. So, you are very, very quickly going to decide which piece of art was created by a human. Left or right? Is it showing?
It's showing, but it's tiny. But it's okay.
Oh, okay, just look at it on the screen instead of on your screen. Or you can click on it and I think it's bigger, but try to do a gut feel. Don't like analyze it. Just gut feel which is human.
Well, it's quite.
Okay, I'm going to go to about maybe. Okay, great. Next one. Which artwork was created by human? Left or right? Look on the screen here.
Screen, yeah.
Okay, it's okay. So what computer can draw like Picasso? Can they draw like Velázquez?
Turns out they can draw like anyone you want. How about this one?
It's fun. I mean, we're all going to pick the less abstract ones for humans.
Ah, this is a hard one. Okay, everyone's done. All right, let's go. I'm going to go back to the beginning.
It's a half and half.
So the interesting thing is, look how close these numbers are. 27, 21. Left, that was created by human. I like this one much more. Just by the way, I'm on the side of the machine. Created by human. Left. It's this one. Well done. So, machines can produce art that is indistinguishable from human art at some level. So there's also ones where you can apply artistic styles to other images. So there's also ones where you can apply artistic styles to other images, which is also amazing.
Amazing. So it can be figurative. It doesn't have to be abstract. You're saying.
Yeah, you can also, but it's not that good yet. So generating it from scratch, so this is generated from scratch. Like it's got a training set, and it's called a generative adversarial network, and it has this creative component on it. So it's specifically allowed to be creative, so it doesn't have to be exactly like what it's seen. And then it produces this art. Another one I like. Is there a way to turn up the volume?
It should be volume.
There you go. This is created by a machine. So it's given Chopin's music, and it's a recurrent neural network again, and it generates music in the style of Chopin. And you can generate in the style of quite a lot of different artists. And I mean, if you hear it, it sounds beautiful. It's very pleasing. This is my favorite one. What they did was they took, again, a recurrent neural network, took a huge body of sci-fi films, like, I don't know, 1,000 films, the full scripts, gave that as training data, and told it to generate a script for a movie. Okay, so I've put about 30 seconds on here. Listen really, really carefully.
In a future with mass unemployment, young people are forced to sell blood. It's something I can do.
You should see the boy and shut up. I was the one who was going to be 100 years old.
I, I highly recommend watching the whole thing. It's about 10 minutes long. It's well worth it. It's very, very funny. But like this is a segment of the script. So we just saw this. I was the one who was going to be 100 years old. But some of it's quite dark in an obscure way. That was a big, honest idea. I am not a bright light. You know, it's very moody and dark. But anyway, this is completely amazing that we're actually at this point where, I mean, computers are being creative. They're inventing stuff in our image, but it's quite amazing. This is also a very profound one. This made a lot of headlines. You might have heard about AlphaGo. So chess, we already know that there are algorithms that can beat humans at chess. And this has been around for years. Chess is actually a much easier problem than a game like Go. So chess has a fairly large, finite number of moves, possible outcomes after each move, right? But it's small enough that algorithms can reasonably search, make good predictions on future moves. Go is not like this, because for each move, there's something like more possible combinations for the outcome of the board than there are atoms in the universe. It's an incredibly difficult problem to solve. It was seen that this was one of the most challenging problems for artificial intelligence, was to beat a human at Go. It's seen as a game that requires intuition more than skill. That you play lots of games and you develop an intuition for what's the next move. And so DeepMind, which is a subsidiary of Google, developed a deep learning algorithm that used this thing called reinforcement learning. So it had recordings of loads and loads of games played by humans, and it also played against itself millions of times. That's kind of what reinforcement learning does. And this is a picture of it beating one of the best players in the world, arguably the best player in the world, for the first time. And apparently there was a moment in the game where the algorithm made a move that was weird, obscure. No one had ever seen a human make a move like that. They thought, this is stupid. This is ridiculous. Why would it make this move? It's going to lose. And it won, of course. And then they looked back and they thought that move was the reason why it won. And it had done something that no human would have done, completely unexpected. And one of the commentators called it the most beautiful move he'd seen in his life, done by a machine. The scary thing is, a couple months ago, DeepMind announced a new algorithm called AlphaGo 0, which doesn't use any human training data and has already beat AlphaGo 100 to 1. So I don't think they've had a big play against a human yet, but basically this problem is now well solved by a very powerful algorithm. All right, so where does this leave us? Does the future look like this? Are we, in fact, enabling our future overlords to come and take over and kill us all? So like quite often you see these amazing results with machine learning, but quite often it can do really stupid things, like the thing with the tanks that I explained this morning. So, maybe we shouldn't be so scared. Maybe the future looks more like this. This is actually a robot my husband and I built, and I programmed his brain. And this wasn't the robot's fault. This was my husband driving forward instead of doing what he was supposed to do. Poor little guy. I like to think the future might look something like this. Maybe the machines are really going to help us reach the stars and help us in all the things, all the problems that we haven't managed to solve yet, and really assist us in achieving all of our dreams. So that's where I'd like to leave it. Thank you very much.
Perfect. Thank you very much.
Do you want to?
It's very hard to conclude something on top of that, but I'd just like to show a couple of things.
Do you want a summary slide from me? I can do it. I've got one. Yeah. Okay. Do you want me to do that first?
Sure.
Yeah. So just to finish off, I also got I've also got a summary slide, just like the others. Kind of main key takeaways, I'd say. If you can use Bayesian statistics, just do it. Don't try to force yourself to use machine learning when statistics will work. Sorry. So, and the regime where you want to use machine learning is if you don't have a good model, but you do have a lot of data. So you're in the regime where you can be data-driven. Machine learning can be a very powerful tool. So if you remember, feature extraction is an important step for standard machine learning. For deep learning, you can get away with not doing it, but you have all the other headaches. And it generally requires some domain knowledge. Right? And try lots of different feature extraction methods, see what really works. So machine learning automagically, that's not a typo, it's a word I like. It automagically builds models, very, very flexible models is kind of my personal definition of machine learning. And there are loads of algorithms out there. You all played with quite a few different ones. And if you're just starting fresh in a problem, I would say random forest is a great one to start off with. It usually works pretty well out of the box. Always keep your test set aside. This is really, really, really important. Keep aside your test set. Don't make decisions based on your test set. Keep everything in your training set and use your test set really as what it's supposed to be, which is test. Test that your algorithm is doing the right thing. And always think about your metric, right? This is very common in machine learning papers to just use whatever metric. They'll just use accuracy, or sometimes at least they'll use ROC curves, which are good. But your particular problem might need a different metric. So always think about your science. Don't think about just this, I just want to do machine learning. I don't care what happens. I just want to do machine learning. Think about your science goal. Let that drive all of your decisions. And I'm sure I've proven to you that deep learning can do some pretty amazing things. So I think that would be my summary of the day. Thanks very much.